Yeah, evening. Zaid Hassan, welcome, welcome. Dorisian, hi, hi. Zobudas, hi. Abdi, hi. Please, let's log in, let's log in, let's log in. Let's come on board. We finish. Yes, Moses Mumo, hello, hello. Let's come in, please, so that we can save time. We are trying to finish whatever we started. Thank you so much. Thank you so much, my students. Welcome on board. Welcome, Cecilia. Hi. Please welcome on board so that we can finish the remaining bit. Then tomorrow you people can revise and then the cut will be very easy peasy. So welcome all. Welcome, Evans. Hi. Today we'll take a little bit, not much time, because I should start straight so that others can join. You think so? Because it's already a weekday and we had lectures during the day for the other students who are not on trip. So people might be tired. That's why, Santino, welcome, welcome. That's why I like weekends. But now we have to finish the remaining bit. Welcome you all. Thank you so much. Thank you so much for coming back on board. Glory, hi. Let us do it together. In a few weeks' time, you'll be done. So let us put the effort for the last time. And then when the exam comes, things will be fine. Hi. Yeah, please. I give 5 minutes. By 9:15, I'll start because the students wanted me to start at 8. I couldn't manage at 8. I already told apologies to my class rep, the other BCHD who is on trip. So I'm sorry about that. But I would like to recover the time because today I have to finish. So you'll just pardon me. We'll start and then the others will join. Just a suggestion. Somebody can say whatever they think because I need to start. What do you think on the same? We can just proceed and then they get us as we proceed. I think that is the best. Yeah, the number is increasing. I appreciate. Let's log in, please. And somebody just tell me what you think because I'm going to start right now. Just say something. If we should start. I've not seen any of the class reps, if they're there. BMLs, are you there? BCHD, all the years, the intakes who are doing biochemistry. I'm going to start, kindly. So, if I could remember well, we were at number 10. So, we're already starting so that we can save time because it might take us longer than the stipulated time, 1 hour. So I request to start. So question number 10, I'm going to repeat question number 10 because it found when I already drew a tetrapeptide Davy. And I told you that I'll always test it in short answer because I will not bring you a question in short answer telling you to draw for me cysteine, serine, valine, for example, but I'll use a peptide, be it tripeptide, be it tetrapeptide, be it pentapeptide. I'll use a peptide so that I can test if you can draw the structures of amino acid, if you know how to draw the peptide bond, do you know the 1-letter code? So I'm testing a lot of things in one question. So in such a case, I also mentioned that when you talk about a tripeptide, a pentapeptide, a tetrapeptide, it relates to the number of amino acids involved in the formation of the bonds, not the number of bonds which are forming, not the number of peptide bonds which are forming, but the number of amino acid involved in bonding. So let us repeat again the Davy. So I already gave the example of Davy, but I'm going to do it. And then I told you that you can try also at your own time using any of the names of yours if they are already in the 20 amino acid 1-letter code. So D was for aspartate. I told you if you see such a question, draw the individual amino acids. We are drawing aspartate. That is aspartate. You'll already get 1 mark. We are drawing alanine. Alanine is aliphatic. We are drawing valine. Aliphatic, but then falls under branched chain amino acids. Then lastly, let us draw isoleucine. I don't know if today my board is visible from all the corners, but I'm going to check. Isoleucine. Drawing each of those amino acids, you shall score 1 mark each. It means at that point, good. The board is visible, but then I can try to put much so that the V, good. So you can see the aspartate is there, alanine is there, valine is there. Oh, Paranai, yes. Welcome, Angeline, welcome. We are proceeding. I've started by the question which we did last time where we stopped. So if you see any of the peptide which you need to draw for me individual amino acids. You'll be able to get a mark each for that. And then I said for a peptide bond, carboxyl terminal end of one amino acid and amino terminal end of the other, water molecule is released. Carboxyl terminal end, amino, another water molecule is released. Carboxyl and amino terminal, another water molecule is released. So what it means here is you shall have already gotten the 4 marks. If you draw all the 4 correctly. If you draw any 3 correct, you shall have already gotten your 3 marks. If you draw any 2 correct, you'll get 2 out of 5. So that's why it's important to draw the individual amino acids. I'll be able to give marks for that. So let's draw the peptide bond for Devi. So we start. The way it is arranged, don't arrange on your own, please. You should arrange it the way I've put it. If it's Devi, you have to start with a D. Carboxyl terminal end of aspartate, amino terminal end of alanine. Simple, simple, my dear. If you know how to draw structures, then you can score everything in my exams. Very important. That's why we talk about, the title is always structure of biomolecules. We focus much on the structures of the monomers. So then we come to the valine. Then carboxyl terminal end of valine, amino terminal end of isoleucine, So the peptide bond will take a half. The number of water molecules will take another half. So you will have 5 marks complete after you put for me 3 molecules of water. The peptide bond, you can see carboxyl amino, carboxyl amino, carboxyl amino, carboxyl amino. So what we are talking much about a peptide bond, it will always involve the carboxyl terminal end of one residue and amino terminal end of the other. At that point where the carboxyl and the amino terminal end is forming a bond, which is a peptide bond, it means a water molecule is released. Can you see? Oh, Tabitha, good, welcome. Can you people see the board? Just tell me. I think I've tried to put it right. Tabitha, yes, hi. We already started so that others can join. I hope everyone can see. So you have to draw the individual amino acids first. It will give you a 1 mark each. Then when you're drawing the peptide bond, Put it the way it has been put, that position. You see? In between there. Don't put it to the north. Neither should you put it to the south. You know what I mean? Just put it where it is, to the east. It has to be in between there. We are talking about the horizontal. So it has to be there. So that you can place very well the bonds around the carbon, the bonds around the nitrogen, and then the R side chain. Some of the books will place the R side chain down here. Some will place it up here. Then hydrogen will come down. It is still okay, as long as you don't confuse it. So the R side chain, when it's below here, it's easier to draw the peptide bond. So let me draw Agnes now. Second example, so that we'll be able to understand. When you see the peptide, I'm going to set it. It has to be there, whether exam or cards, but you won't know which one. So I can give any of the examples as long as you know the one letter code for the amino acid which I've given, as well as the 3-letter codes, the R side chain, you draw it correctly. So we are drawing a pentapeptide. Agnes, yes, Agnes has, I think it is, that is 5 letters. The 5 residues are involved there. We call it a pentapeptide. You start with alanine, then you do glycine, then you do asparagine, you do glutamate, then you do serine. So when you start with alanine, alanine we know, CH3. Glycine, the simplest of all, you do NH2, it is H on the R side chain. Asparagine is amide of aspartate. You will do CH, COOH, NH2. You will do aspartate, glutamate, sorry. I have to see how this one shows before I can draw the pentapeptide. That is glutamate. And then serine is the alcohol containing one, CH2OH. Drawing the individual amino acids will score you a mark each. In that case, you shall have already scored. Oh, thank you. Murungi had to confirm if it's visible. I'm happy. So look at that. Alanine, glycine, glutamate, serine. Yes. Draw individual amino acids. Individual amino acids. It helps. Now I'm going to draw the peptide bond. Individual amino acids. Alanine there, glycine there. The way they appear, asparagine there, glutamate there, serine there. Then let us do the peptide bond. Here you shall have already scored 5 out of 6. So that if you don't get the structure of asparagine right, then you shall get the other 4 correct. 4 out of 5. You shall have already gotten something. I still repeat, don't go straight and draw the peptide bond without the individual amino acids, because you'll always score a mark based on each of the amino acids you draw. So if you look at this, we are going to draw the peptide bond. At the point where we have the peptide bond, I'm going to highlight using a green color. So let's start amino terminal end. And then we have the carboxyl terminal end of alanine, carboxyl terminal end, alanine, amino terminal end of glycine. Simple as that. Carboxyl terminal end of glycine, amino terminal end of asparagine, Carboxyl terminal end of asparagine, amino terminal end of glutamate, carboxyl terminal end of glutamate, amino terminal end of serine. And then you will have to put plus 4 water molecules at this point. 1, 2, 3, 4. 4 molecules of water. Imagine 6 marks already there. Simple as that. Yes. So we are talking about the carboxyl terminal end and amino terminal end, carboxyl terminal end and amino terminal end. At that point where the carboxyl and the amino terminal end of 2 amino acid residues is involved in the formation of the bond, a water molecule is released. So let me check where I am now. We are talking about pentapeptide agonist, tetrapeptide Devi. We already done those two. Number 12 says aspartate and lysine. Excuse me, madam. How do we draw a peptide bond in structures of amino acids like tryptophan and histidine? Correct. So whatever happens, Evans, if you see such a question, which sometimes will be challenging, because if you look at the peptide bond in histidine, most of it, the R side chain, the CH, you see where the CH2 is. That is why it connects. But now you will put a less carbon, a less bond, as long as the carbon is balancing and the nitrogen, even if it means that you are going to have one bond less. It means the main issue here is we have to balance the bonds, because the ultimate goal of a peptide bond is the carboxyl terminal end has to attach to the amino terminal end. Yes, Kelvin Kome, hi. So if you look at the R side chain of tryptophan, in fact, tryptophan is even easier because the R side chain separates well from the carboxyl and amino terminal end. Whatever is complicated is mostly the histidine, because you'll find where the first cyclic form, where the cyclic form is, the carboxyl terminal is connected. There is a nitrogen which is connected there. So as long as you have to balance the bonds around the carboxyl and amino terminal end, it will still enter, because those histidines still form the components of the primary structures of some of the proteins. So the main idea here is, yeah, Mohammed, welcome, my dear. The main idea of a peptide bond is the carboxyl terminal end. Please spare us on that, madam. Of course, Paranai. And that is why I said I don't make life horrible. No, I will not. I will not do that. That's why I escape histidine and tryptophan, even in peptide bond. I know. I'll spare you that. But I'm trying to explain a point to Evans that a peptide bond, it will always involve the attachment of the carboxyl and the amino terminal end. Because when you look at the primary structure of those proteins, it is a 20 amino acid. None is excluded, depending on which protein it is. Because the histidines and the tryptophan, they'll also play a role in the structure of those amino acids. So the main objective here is we have to talk about attachment of the carboxyl terminal end of an amino acid and amino terminal end of another amino acid residue for a peptide bond to form. So Paranai, no, I promise in my own name The tryptophan and histidine, I'm not going to include it in the peptide bond, but it's very important to understand. Very true. Thank you so much. It is very important to understand the concept of a peptide bond. And a peptide bond will be found in protein, while the glycosidic bond will be found in the carbohydrates. So we can proceed. Don't have a headache and don't have sleepless night on that. I don't make the life of my students horrible. No. I already know the complication on the structure of tryptophan and histidine. But the main idea is the balancing the bonds around the carboxyl and the amino terminal end. Thank you so much. So we can move to question number 12. It says, I'll be able to answer in the chat. If you have something which is not clear, we'll be able to highlight it, please, before Friday. Aspartate and lysine are two different amino acids. We are still on our question number 12. Classified based on their R group or side chain. Mention the groups and structurally differentiate between the two. So mention the groups they fall under. That is very easy. And for me to set a question like that, I don't think that I can set, but it's good. I've already put it as an example here. Maybe somebody can also learn something from it. So if you check at aspartate, if you could remember well, we had the carboxyl, the acidic amino acid. They have the carboxyl group on the R side chain. Aspartate and glutamate are falling under that class. So you talk about the acidic amino acids. And then the second one is glutamate. So just whatever is on the board, but then let me put it clear. Let me just rub it. So lysine was falling under basic. And then glutamate and aspartate was falling under acidic. Sometimes somebody can talk about diamino, dicarboxymonoamino. I'll still give you a mark because you have an idea. That is for aspartate. For lysine, you can talk about diaminomonocarboxy. I'll still give you a mark because you have an idea. You can't give such a student a wrong because it's correct. As much as we know, under the R side chain, they fall under, aspartate will fall under acidic amino acids. And that is the structure of aspartate, the presence of COOH. And then you have lysine, which is a K, which looks like this. So we have for the CH2s, the presence of the NH2 will give it a basic property. So you talk about the first one, that is aspartate, the presence of acidic group. Excuse me, madam, draw one including like tyrosine, kindly. Okay, I'll do that. I draw a peptide with tyrosine, and let me remember any. So tyrosine is Y. I want us to draw. Let me finish with this, then I will draw, Glory. So what we have there, question number 12, aspartate, acidic, look at the COOH. They will always be proton donors, as we describe, simple description of acidic or acids based on Bronsted-Lowry theory. And then lysine is basic, proton acceptors, still the simple definition of bases based on Bronsted-Lowry. So that is what I need there. So if you mention that acidic amino acid, 1 mark. Then you give structure, 1 mark. Lysine, basic. You give structure, another mark. You can talk about dicarboxylic mono amino. I'll still give you a mark because you are right. Whichever way you try to give me the class, whether nutritional classification, I will not deny you any mark. As long as you give me the correct thing, I will give you a mark. But then the answer directly should be acidic and the other one is basic, and you draw the structure. Glory has requested a peptide which has tyrosine in it. I want us to draw it which has a Y. I always like crazy things. Can I talk about say, for example? Say, yes. We are going to draw a tripeptide say. She said one with the tyrosine. Say. I told you I'm going to test them using a peptide bond. Say. So you have to draw serine. Start with serine. Serine is here. CH2OH. Alanine is here. Alanine. And then tyrosine looks like this. Remember, it's a Y. Tyrosine. Tyrosine and phenylalanine look alike. The difference is only tyrosine has OH down there. I'm going to draw that. That one is easy to draw. Only tryptophan and histidine. Even proline is not complicated. Proline is not complicated. Because at the point where we have the carboxyl, the amino terminal end, we just have to balance the nitrogens there. Yes. So that is how the 3 amino acids where tyrosine is. Enoch, hi. Moses, Mumo. Oh, Sally. You wanted me to draw Sally. Yes, we can accommodate Moses' idea. Leucine. Good. Let us add leucine. Moses, we are going to draw Sally. Very good. I was always telling you to use a name. We do Sally. We do Sally. It's okay. We are going to do that. Worry not. Sally. So we do leucine first. Let's do leucine. Then we can finish with our tyrosine. Leucine. Let's do leucine. Then tyrosine will come here. Tyrosine. And then I want to try one with proline. I want to try one with proline. Think of a name. Think of a name kindly where proline is. You can even tell me Penina. Penina is very long. I don't know whether our board will be too much. But then remember where proline is as we proceed, because Moses said Sally. So with our Sally, look at that. You start with serine. Then you do alanine. You do leucine. You do tyrosine. We are going to draw the peptide bond now. In fact, that is a tetrapeptide. 4 amino acids are involved. We are going to release 3 molecules of water. Let us draw. Carboxyl terminal end here. I'll make it a bit, because it's a bit down, so I'll need a space. But let's start from here. Amino terminal end of serine. Then we have the carboxyl terminal end of serine, amino terminal end of alanine. Very interesting, my dear. We are simplifying biochemistry, and that's why the channel says biochemistry simplified. Let's simplify it. So, carboxyl terminal end of alanine, amino terminal end of leucine, amino terminal end of leucine, amino terminal end of leucine. Then we do carboxyl terminal end of leucine, amino terminal end of tyrosine, amino terminal end of tyrosine, amino terminal end of tyrosine. There is an OH down here. If you don't put an OH, it will show that you've drawn phenylalanine. Simple as that. That is Sally. Peptide bond, you can see the carboxyl terminal end. Tip. Very good. We'll do tip. Yes. I want to draw proline. So in that case, whatever you can see there is very simple because you have to match the way they are showing. You have to match very well those amino acids showing one letter code, showing a peptide bond, how a peptide bond looks like. And you should also not forget that at the point of peptide, is it possible for you, madam, to draw Marcy? Why not? It is possible. Very much possible. Because, yes, because at the point, are there situations where, let me answer this first. When you look at arginine, yes, when you look at arginine, try to check at the amino and the carboxyl terminal end. If the R side chain is free with its own structure and the carboxyl terminal end and amino terminal end is intact, as long as at the point the peptide bond is forming, the amino terminal end will be able to connect with the carboxyl terminal end. Then the R side chain, even for that arginine, which has the R, the CH2s, there are like 3 of them, and then unapiga corner with an NH. As long as the carboxyl and the amino terminal end, Terry. Yes, that is 2 of the arginines, 309. How will R get HAPO? Huh? Oh, wait. I'm finishing. Mighty Leshan is talking about Mercy. So where the challenge is coming for Leshan is where arginine is. I can see the headache is coming on arginine. I think I'm correct about that. But what you have to remember, that if you look at the carboxyl terminal end of arginine and the amino terminal end of arginine, it is free. So as long as the carboxyl terminal end and the amino terminal end can connect, it is easy to draw the amino acid. The reason why we are talking about tryptophan is at the point the tryptophan is forming, it doesn't have a free R side chain, a free carboxyl terminal end, sorry. So for arginine, there is a free terminal end there. Remember, there are whatever we drew in the body in class, we had CH2. On the R side chain, there is free amino terminal end. And then, ilipiga corner, there was NH. And then we had a C, and then an NH2 and NH3. If I can recall the structure, there were 3 of those CH2s. So as long as that structure, there is a free R side chain somewhere, there is a free amino terminal end, then it is okay. So let me draw the one which was said first, tip. Was it the tip which was said first? The person for tip came first. But what I'm still saying is, it is good if the amino, you see how free the amino terminal end is. So if you look at the one for arginine, what I drew in class was something like this. There were CH2s, 3 of them, and then there was in fact, it was like this, CH2, and then there was an NH, ikipiga kona hapa. Then there is a CH. Then there was another NH, not sure, and then NH3 plus, something like that. So as long as at a certain point, the amino terminal end was free like that, and the carboxyl terminal end was free, and then you had the C and the H up here. So you'll be able to connect. Here is where you connect the peptide bond here. This R side chain doesn't matter. That one you put it wherever it belongs to. Whatever matters is the carboxyl and amino terminal end when we are forming that bond. The carboxyl and amino terminal end. So let me draw tip because I'm interested in proline. Let me draw tip. So you'll do 309 first. 309. You see, if as long as this side and this side is free, it's easier to connect the amino and the carboxyl terminal end. That is 309. And then we do isoleucine. It is the isoleucine. Sorry, I don't want the green one. Isoleucine. The connection of amino and the carboxyl, very important. That is how a peptide bond forms. The R, it has to remain the way it is. Because even when you're drawing the peptide bond, the R has to retain its structure the way it is. Now proline looks like this. That is where I wanted the challenge to come clean to my head. Proline has something like this. Proline has something like this. Proline. What I know, there are 3 of the CH2s, and then it connects here. Are you getting the point? That is proline. So it means for you to draw a peptide bond, this H has to go away. And I'm going to draw it. So we are trying to find, look at that. Yes, Charity, hi. I'm trying to work on the proline. Look at the proline. Whatever some books draw is NH2. But remember, if you put NH2 on that amino terminal end of proline, you have to add a plus because we are talking about less one hydrogen. For it to balance, nitrogen we said, and we agreed, and we are still agreeing because the periodic table still retains the same story. Nitrogen being atomic number 7, configuration will go to 2 to 5. So it means the bonds around the nitrogen, they have to have 3 for stability. The outer shell need 3 for stability. So to avoid most of the confusion, leave it NH, meaning that for it to have the 3 bonds, it's something like that. So just leave it NH. Leave it NH. We are going to draw the peptide. The tripeptide tip, this is how we are going to draw it. And I told you for all of them, check the amino and the carboxyl terminal end. So it will start like this. That is 309. 309 was alcohol containing. Then carboxyl terminal end of 309. Amino terminal end of isoleucine. Isoleucine. And then we mention now carboxyl terminal end of isoleucine and amino terminal end. It will look like this. Imagine, it will look like this. It has to look like this. It can't look like any other. So it has to look like this for us to balance the bonds. It has to look like this for us to balance the bonds. It has to look like that. So you have to check if the bonds are balanced. 1, 2, 3. It can't be more than that. So it has to remain like this without a H. If you put a H, it will be excess. And then you talk about true water molecule. That is how proline will look like. So the carboxyl and amino, carboxyl and amino, carboxyl and amino, and make sure the periodic table still have to work. Atomic number, balancing the bonds around the carbon, balancing the bonds around the nitrogen, balancing the bonds around the sulfurs, whichever way. So even in this theory, the arginine, as long as the carboxyl and amino terminal end can be left free and you connect the carboxyl and amino, it is possible. But still, as I mentioned, that's why you can see I'm also trying to escape with the students the ones which are complicated, like the arginines. I don't want to break my promise for Kanai. What was the name of that student who chat and said, Madam, please, don't bring for us the complicated stress ones. The main idea, and what Moses was also wondering about, the main idea here is there is a free carboxyl terminal end. There is a free amino terminal end. Can they combine to form a peptide bond? Because the carboxyl terminal end of a residue and the amino terminal end of the other, at that point is where the peptide bond forms. And at that point, a water molecule is released. So don't fear anything. If you know we have revised thoroughly, and you are there when you are revising, imagine passing the CATS and main exam will be very easy. And at that point, when something is not clear, please just raise it. I'll be able to answer. Question number 13 says that you draw structures of any three monoamino monocarboxylic amino acids. Such an easy. Please don't set it. No, don't talk about setting. Let us revise. Moses, let us revise. I already said I always don't make life horrible for students. For the ones who have passed through my hand, yes. But it is a duty of the students to study. Let's study and understanding the concept. Very important. We don't want fear. Leave fear out. Huh? Let us proceed and see what we have to discuss as we proceed. So I'm talking about monoamino monocarboxylic. Okay. Tell me in the chat. Examples. Monoamino monocarboxylic. In fact, they're almost whatever is on the board. So they have one carboxylic group and one amino group. So you can draw any three. So whatever is on the board, you can start with whatever is on the board, but then you know monoamino monocarboxylic. If you look at the aliphatic amino acids, yes. If you look at the aliphatic amino acids, and then you look at the alcohol containing, and then you look at sulfur containing, those are all monoamino monocarboxylic. And then you look at phenylalanine, you look at tyrosine, so you can draw any. In fact, in the aliphatic, you can draw glycine, you can draw alanine, and then you go to alcohol containing, you can draw the simple structure of serine, you can go to sulfur containing, you draw a simple structure of cysteine. So there are a lot. So each of those can give us 1 mark. And then we are almost in the short answer. Then we can, you know, the good thing with this is it finds when we already discussed some up there. So we'll be able to move a bit faster. And then the other one says, draw all diamino dicarboxylic. And then monoamino dicarboxylic. It is simple. What I need there is acidic amino acids and their amides. Simple as that. Each of them will be 1 mark. Diamino dicarboxylic amino acids, the 1 to the 2 amino group, 2 carboxyl group, we have asparagine and glutamine. And then dicarboxylic monoamino, we have glutamate and aspartate. Simple as that. Now we can draw the aspartate, we can draw the glutamate, you can draw glutamine, you can draw asparagine. So those are the dicarboxylic diamino, mono, amino dicarboxylic. Yeah, somebody says, pardon, number 13. Yes, I will. Number 13. It was talking about 3 homogesty. It was talking about 3 monoamino monocarboxylic. And I said homogesty. I said there are examples are a few on the board. If you talk about monoamino monocarboxylic, they have 1 carboxyl group, 1 amino group, 1 amino group, 1 carboxyl group. Even this one amino group, 1 carboxyl group. So just by example, I said that we are talking about example of the amino acid. They could be aliphatic amino acids, if you like. They could be alcohol-containing amino acids, if you like. They could be sulfur-containing, if you like. Even the aromatic, they could be those. But specifically, if you want, easy one to draw, phenylalanine and tyrosine. So if you look at the general structures of the amino acid, we only have 1 carboxylic group and 1 amino group. Majesty, did you get it? We are moving to essays. Whatever we've discussed, but we are going to stress much whatever we didn't get right, because most of them we've discussed in the short answer. So we are just going through them and try to remind ourselves what we've done. So question 15, using 4 structural examples in each case. Let me read it well because I wasn't seeing. Using 4 structural examples in each case, discuss the 2 criteria which naming of monosaccharide is based on. That is like I'm giving free mark. Imagine. You start by 1 telling me that monosaccharide criteria for naming of monosaccharide, 1 functional group. And then in the functional group, you have to explain about the aldoses. And you have to mention at carbon atom number 1, they have the aldehyde group. Oh, good, Kim Tai. I'm very happy, my dear. Oh, yes. Blessings. Thank you so much. And congratulations. You passed with A's. Please, I always want you more people to come. The alumni of the channel, you come and you say your testimony. It encourages the other students. Thank you so much, Kim Tai. I'm happy. Stay blessed. But you can still listen and encourage the other ones. Yeah? Thank you so much. So we are talking about question number 15. You are mentioning 1, the first criteria, functional group. And in functional group, you have to say that the aldehydes, aldoses, the aldehyde group at carbon atom number 1. You have to specify at carbon atom number 1. And then you give examples by drawing structures. So it means at that point of the aldehyde group, the aldoses, I'll need 4 structures. I said 4 structural examples in each case. I need 4. So you have to draw for me glucose. You can draw for me galactose. You can draw for me glyceraldehyde. You can draw for me ribose. That's already 4. You'll score a mark for the 4. Explaining the functional group and the carbon atom, you shall have already gotten 2 marks. Then you go to another functional group, ketosis. And you have to mention at carbon atom number 2. Because remember, the question is 20 marks. Each of those facts will contribute to a mark. So at that point, I need the structure of fructose, be it D or L, it doesn't matter. As long as you draw the linear form, don't try to draw for me the cyclic form, because it will not bring clearly the keto group, neither will it bring even the number of carbon atoms. So it has to be in a linear form. You can draw for me fructose, you can draw for me ribulose, you can draw for me dihydroxyacetone, you can even draw for me erythrulose. I don't have any problem. As long as you draw for me 4 of the structures, for ketosis, 4 of the structures. For aldoses, mention the functional group. And do you know how simple it is to draw those structures? If you know how to draw glucose, drawing glyceraldehyde is easy because you'll know automatically the carbon atom number 1 will have the aldehyde group. Let me draw it so that people will not say, Madam, you did not draw, you are just mentioning. No, we are going to mention as we draw. So if you start with the 3 carbons which have the aldehyde group, it looks like this. The first carbon has to have the aldehyde group. The last carbon is CH2OH, glyceraldehyde. Simple as that. Then you come to erythrose. Just rub. Imagine, that is how simple it is. CH2OH. Come to ribulose. Just rub. That is the third structure. Sorry, I don't want to use green. Come to ribose. Sorry, do this. 5 carbons, but the last one is CH2OH. The first one is aldehyde group. Then now you come to our glucose. But then go straight up here at carbon atom number 3. Imagine, that's how simple it is. The last carbon for all these monosaccharides will always be CH2OH. It doesn't matter. So the carbon atom number 2 in keto will have the keto group. The carbon atom number 1 for aldoses will have the aldehyde group. That is the same way when you want to draw the one for ketosis. The first one will be CH2OH. Second one, keto group. Third one, OH. And then the fourth, fifth, the sixth one will be CH2OH. So if you talk about the functional group, give me that one. That is fructose. And then now you want ribulose. OH this side, but then CH2OH. Then you talk about erythrulose, CH2OH. What is difficult there? Dihydroxyacetone, CH2OH. So based on the functional group, we have ketosis. Carbon atom number 2 carry the keto group. Based on still the functional group, carbon atom number 1 has aldehyde group. They are known as aldoses. Simple as that. And draw structures. You will get your marks. The other criteria is based on the number of carbon atoms in the main skeleton. And that's what I've been drawing on the board. As much as I've been stressing much on the functional group, but if you look at them, I start with 3 carbon, 4 carbon, 5 carbon, 6 carbon. But you have to mention that 3 carbons are trioses. That will give you 1 mark. 4 carbons, tetroses. 5 carbons, pentoses. 6 carbons, hexoses. Then when you draw those monosaccharides, you have to mention, give their names. Because the names also are going to give you mark. If it's galactose, if it is glucose, if it is xylose, if it is ribose, if it is ribulose, if it's ribose, it is going to give you a mark. But then remember, we are talking about naming of monosaccharides based on the functional group. We've already expounded on that and the structures. Based on the number of carbon atoms, the main skeleton will give you a mark, but then each one of those will give 1, 1, 1, 1. Then draw structures of those 4. You will get full marks. The question is 20 good marks. So we have to utilize the time. We have to utilize the marks well. Some students are already tired when answering. So what they give me is, I ask about the criteria, they combine the number of carbon atoms and the functional group because they're tired and it's madam who need answers. So they draw for me 4 structures and it's done. They don't want to draw anymore. I just give marks for whatever you've drawn for me. You will just get like 4 or 5 marks than somebody who has gone to draw for the ketoses, 4 of them, aldoses, 4 of them, number of carbon atoms, 4 of them. That already somebody has scooped 12 marks. And then now explaining, it will add, the 8 will come on automatically. So you can't give less structures and you want me to add into my mind and fill the gaps that, oh, this student meant the same, so I should give 2 marks. It represents the number of carbon atoms and the functional groups. No. That is your day. The 2 hours is your time. Take time. Write everything which makes sense because we're not going to write it anymore. And it is going to give us all the marks. So if you see the marks, it relates with whatever you are going to write. I don't say that you write like 10 pages, something which doesn't make sense. No. Just write sensible things, but answer as per the question. Derive the Henderson-Hasselbalch equation. As simple as that. Sometimes I always reset the question by saying, derive the equation which is used in preparation of in the lab. That is the equation which is used in buffer preparation in the lab. So if I talk about the Henderson-Hasselbalch equation, we are talking about the buffer. But then, when you talk about the buffer, remember the components of a buffer is a weak acid and a conjugate base. So it means we are going to talk about the dissociation constant Ka for the weak acid. And it has to start by talking about the weak acid, which is Ha, which dissociates to hydrogen plus or the proton and the A minus. This is the conjugate base. This is the weak acid. We talked about Ka in class. So don't confuse Ka and Keq. They don't match. So what we always say here is, if you look at Ka, you will equate Ka to Ha, concentration of the weak acid, over it is the other way around. Where is my rubber? The concentration of H, hydrogen ion concentration, over the weak acid concentration. So you have the conjugate base, you have the hydrogen ion concentration over the weak acid. And what I said that first, you have to make the hydrogen ion concentration the subject. So we say make hydrogen ion concentration the subject. My body is too small, but what I'm going to do it here. So whatever we agreed is, whatever you do to the right, you do to the left. And then if you cancel, next you'll be having hydrogen ion concentration, conjugate base concentration equals to Ka H A concentration. But then, since we need to make hydrogen ion concentration the subject, whatever you do to the right, do to the left, sorry. Whatever you do to the left, you do to the right. So you will cancel the conjugate base with the conjugate base. This side, we will have hydrogen ion concentration equals to Ka Ha over A minus. And then you do there, we already made hydrogen ion concentration there, the subject. You introduce logs. So you have the notes in class, but then we are going to remember bits. It will force me to rub this side, but then I'll go the other end so that we can see until the end. So we are talking about log hydrogen ion concentration equals to log Ka. In between, there is a multiplication, so we'll say plus log Ha over A minus concentration. And then you introduce negative sign. Negative sign, if it's introduced, you talk about negative log hydrogen ion concentration equals to negative log Ka. Negative and a minus, negative and a plus will be a minus. So it will be minus log Ha over A minus concentration. But what you can see there, something which you know, pH is defined as negative log of hydrogen ion concentration. Then pKa is defined as negative log Ka. That one we discussed in class. So you're going to substitute the pH with negative log hydrogen ion concentration, pKa with negative log Ka. So you're going to have pH equals to pKa. We have minus log Ha over A minus concentration. But then the rule of logs. So when you do reciprocals, the denominator, whatever is down will go up, whatever is up come down. There is a negative sign. So at last, the Henderson-Hasselbalch equation will come to pH equals pKa plus log conjugate base over concentration of weak acids. It's a bit long. Let me see. Okay. Phoebe, I'm going to answer. So we are working on the Henderson-Hasselbalch equation until you have the equation there. But now I'm going to answer Phoebe. Phoebe is saying, hi, madam, kindly clarify that monosaccharides are only. Who said only? Phoebe. That is not what I taught in class. Are only classified on functional group. Who said that? That is not what I taught in class. Functional group and... No, Eunice, no, I'm sorry. The equation is not for you people. Water and buffers, I'm not going to, because I don't teach it in class. I always teach the regular because I can derive it on the board. So you are not going to do equation. Don't make your head go gaga for no reason. So we are not going to do buffers and water for the upgrading, only for the BCHD and the BMLS regular. Eunice? So as for upgrading, I exclude the contents do not cover. Yes, please don't get stressed. Water, though you can just be present, but then if you see something on water and buffers, just ignore, please. Phoebe, I would like to know why you are talking about the only. You know, if you put some English there, it can confuse everyone. You are talking about monosaccharides are only classified. No. In my class, I didn't say that. Monosaccharides are classified based on, the other students can attest that, even the upgrading, that's what I taught, the BCHD, the BMLS. I was expecting other classification. No, it is 2. But you know of the number of carbon atoms, the main skeleton, and functional group, those 2. Though when such question is asked, some students always get confused. They give me an answer of functional isomers and epimers. No, I didn't say that those are classification. What I need is talk about the functional group, the ketosis and aldoses, talk about the number of carbon atoms, full stop. So don't give the cyclic form, don't give epimers, don't give functional isomers. Those are no classification. Those are not classification of monosaccharides. You get? Okay. So that is the Henderson-Hasselbalch equation, the equation which is used in preparation of buffers in the lab. So for the BMLS upgrading, we are not going to set any of these, neither are we going to cover it. Since we don't cover it in our course outline, we exclude it everywhere we go. But it's good to listen. But my BMLS regular and BCHD, the regular students, even if the nursing, even if it's pharmacy, even if it is MBCHB, I will always derive the Henderson-Hasselbalch equation. I'll do water and the pH of water, which is 7. So just ignore for the upgrading. It's okay. Don't get stressed over it. So we are talking about question number 17, Roman 1. Okay, thank you, Phoebe. Question number 17, Roman 1, it says, we are almost, don't worry. Discuss any 2 homopolysaccharides. I think we mentioned, and for the BMLS upgrading, I did heteropolysaccharides, so I might cover them. Whatever I did in class, in the lectures, for any of the groups, I will cover in exam or in CAT. If I didn't do it, I'm not going to cover. That's why you can see for the BCHD, I didn't do any heteropolysaccharide because BCHD are combined with BMLS regular. So if I do the hetero, I'll be unfair to the BCHD students. But if the BMLS are alone, I could cover it because their contents are a little bit different, a little bit. So meaning it's an advantage to the BMLS because I excluded the heteropolysaccharides, even the amides of the monosaccharides, the glucosamine and the manosamine, which we did for the upgrading, it's not here. So you can see any 2 homopolysaccharides, you can describe the structure of glycogen, you can describe the starch, and you still get the 10 marks. So under starch, you have to talk about the amylose and amylopectin, amylose being linear, amylopectin being branched, and then the presence of the more branching, the glycogen is more branched than amylopectin. And then you talk much about how frequent the branches are in these 2. So you talk about still starch, the glucose, storage form of glucose in plants. So those are the things you're talking about. The alpha D glucose, very important to mention. The 1,6, 20 to 30 glucose units where you find branches. So those are the things you're talking about. If you talk about the amylopectin, it is less branched than glycogen. And now you talk about glycogen, form of glucose in animals, and it's more branched than amylopectin. It is also branched, yes. It has both 1,4 and 1,6, and still the alpha D glucose. You might also try to talk much about cellulose because I've said any 2. Cellulose, remember, it has a beta D glucose, and it is linear. It is not branched. So it forms a beta 1,4 glycosidic bond. So you can talk of any. Whatever we did in class, you can talk of any. Just describe it. Don't even draw it. That's why I said discuss. Because also in class, for the regular group, I did not do much of the structures, but I described the structures. So using structures, discuss monosaccharide classification based on functional group. You can see that one you've already covered. So you'll be able to talk about the aldoses, or the ones with the aldehyde group, the ketoses. This one, I just left it open. But nowadays, I always stress using 2 structures. using 3 structures, so that the student will only know to give you 1 structure and expect all the marks. So I always tell the number of structures. In this case, I forgot to mention, but I'll always mention. We are talking about KEQ value of 1.8 times 10 to minus 16. You prove that the pH of water is 7. These questions, either of them, I can't set both of them, but either of them, it can come in the CAT or even in the main exam because I like them. You will either derive the Anderson-Hasselbalch equation in one of the questions, the essays, or you'll always derive the neutral pH of water, which is 7. So let us see how the pH of water comes to 7. And it doesn't even need a calculator. That somebody is entering with a calculator in the CAT because Madam is going to give us. Don't you know that the figure will still come to 55.56? So why would you carry a calculator yet? You are not going to calculate the whole thing. You only have one, which you already know. That is the value. So just by knowing the value, don't come with a calculator where you can put a Mwakenya there in the name of passing a calculator to a neighbor. Don't carry any calculator because you still know the. So we are talking about 1.8 times 10 to minus 16. It has to be the minus. Prove that the pH of water is 7. Remember, we are talking about KEQ. Dissociation constant of water, it comes here. When water dissociates, it is going to give us hydrogen ion and hydroxyl ion. The dissociation constant will come in between the KEQ. Remember, if you put Ka there, that's where the confusion comes. Some students will confuse the Ka and KEQ. Immediately you put the KEQ where the Ka should be, already everything is done. You don't know the type of confusion which will come down there. So you have to know the KEQ will go with water. Dissociation constant of water, and KEQ will always be equated to Kw, which is the autoprotolysis constant of water. We are talking about the protons, the hydrogen ion. So we are saying that 1 mole is equivalent to 18 grams. So you are talking about 18 grams which come about. If you look at the atomic number of oxygen, you know, the formula which we learned in secondary school, if you look at the periodic table, those elements which were having the even numbers, so we talk about 8, 6, 4, 10. What you could learn with their atomic masses was very simple. You just multiply by 2. But the odd numbers, the formula was coming to 2n plus 1. If you look at the odd numbers, the 3, 5, 7. So in this case, we are talking about 2 molecules of hydrogen. You know, hydrogen was constant. Be it atomic number or atomic mass, it's 1. But in that case, we have 2 of them. So it will be 2 grams plus oxygen, the mass will come to 16 grams. If you add to 2 grams of the 2 hydrogens, you get 18. That is what I'm writing there. So what we are trying to do here is, you are trying to find the concentration, just as we had. You know, we had the Ka. Here we'll have KEQ, which will equate to hydrogen ion concentration, hydroxyl ion concentration over the concentration of water. We already know KEQ here, 1.8 times 10 to minus 16. And then you will equate to hydrogen ions, which you don't know, concentration. Hydroxyl ion, concentration, which you don't know. We are looking at, we want to find the concentration of water. And if you talk about concentration, you remember the concentration working on. If you're working on, what did we call it? The mole concept, correct? That is the point in secondary school. You talk about concentration, it talks about molarity, capital M. Or you talk about moles per liter, right? So we are trying to look at the concentration down there. That's why I started with 1 mole is equivalent to 18 grams. What of 1,000 grams per liter? That is what is equated to molarity. So I'm saying that 1 mole is equated to 18 grams. How many? 1,000 grams per liter will give us what? Then you come here, you put 1,000, you cross multiply grams per liter times 1 mole over 18 grams. Let grams cancel themselves. You know, molarity is equated to moles per liter. So you'll ask yourself, 1,000 moles per liter divided by 18. You will get 55.56 moles per liter. It means that is the concentration of water. So you have to substitute whatever is here with this. So you'll say KQ, you already have 10 to minus 16 equals to, you don't know hydrogen ion concentration, you don't know hydroxyl ions concentration, but you know the concentration of water as 55.56. Cross multiply. I'll project my board. 1.8 times 10 to minus 16 times 55.56 equals to hydrogen ion concentration, hydroxyl ion concentration. Whatever we are going to do on 55.56 should be the same as whatever is on 1.8 times 10 to minus 16. We have to put it to base 10, where it's going to be 1.8 times 10 minus 16, and then you will do 0.5556 times 10 to minus 2, which will equate to hydrogen ions and hydroxyl ions concentration. Look at that. The 0.556 sorry, times 10 to power 2, the power is positive. If you are positive, you are going to move 2 steps ahead. So if you move 2 steps ahead or 2 steps to your right, you are going back to our initial value of 55.56. So what happens here is, if you multiply 1.8 times 0.5556, you'll get 1. We are multiplying the decimals, and then the powers, you know what happens there. You have to put a plus because it's a multiplication. So it will come to 1 times 10 to minus 14. But then this one we equate to hydrogen ions concentration and hydroxyl ions concentration. But we are talking about using a KQ value of 1.8 times 10 to minus 16. Prove that the pH is 7. Definition of pH is negative log of hydrogen ions concentration. We don't need the hydroxyl ion. We only need the hydrogen ion concentration. So the ions, we should always divide them equally to a ratio of 1 to 1. So what happens here is, already we have a power 14. It means each one will be 7, 7. But remember, there is a negative sign up here. And pH also is negative log. So we'll do negative, and then the negative up here, the hydrogen ion concentration will take the 7. A negative will cancel a negative, and you will have a plus 7. That is the neutral pH of water as 7. That is what I've done. So we'll have to follow in the lectures in class. The channel has the buffers and waters. Just try to derive any of those equations. The Henderson-Hasselbalch, the equation where the pH water is 7. If you know them, it will be fine. Everything will be fine. I told you, let us sacrifice for the few weeks which are coming, and then after the good thing, the exams are coming. Week 1, all of them, you shall be done with all the biochemistry, my biochemistry in week 1. And we shall be able to be happy to enjoy Christmas if you've written the correct thing. So let us sacrifice for now. What did I think I passed some. I already at 23. Yes. Show a reaction on how water acts as a buffer. That one will always come in 3 marks. So where the 2 molecules of water are involved, and then you form the hydronium ion and hydroxyl ion, that is already enough for the 3 marks. So you have something like this. You know, water will always act as both an acid and as a base. Simple as that, and you'll get your marks. It will be a proton donor. It will form hydronium ion. This will be a proton acceptor, and then it will be less, a hydrogen or a proton. So at that point, that is the equation where water acts as a buffer. Some students will always give me the one where I had, was it, what chloride? Where I was introducing the acids and bases, where I used the hydrochloric acid, and at the point where I used the ammonia. No, it's not that one. It is this one. 2 molecules of water. At a certain point, one will act as a proton acceptor, the other one will be a proton donor, and then it's going to form hydronium ion and hydroxyl group. So that's fine. So we are talking about classification of amino acids based on the number of carboxyl and amino groups, and draw structures of any 10 monoamino monocarboxylic and 2 diamino dicarboxylic, including their 1 and 3 letter codes. Let me read it again. Discuss classification of amino acids based on the number of carboxyl and amino groups, and draw structures of any 10 monoamino monocarboxylic and 2 diamino dicarboxylic. So what I want there is, I already mentioned, you can draw the aliphatics, you can draw the sulfur containing, you can draw the alcohol containing, you can draw the aromatic, as long as they have 1 amino group, 1 carboxyl group. And then all the amides of acidic will be diamino dicarboxylic. And you have to know the 1 letter code, you know, the 1 letter code, you know, the 1 letter code for glutamine. It is Q. 1 letter code for asparagine, it's N. For the other ones, they can be obvious, especially the aliphatics. Nothing changes there. For the alcohol containing, nothing changes there. For the sulfur containing, nothing changes there. Things only change for the other groups. So, in such situations, you can easily scoop marks if we revise and we understand each and every concept. Very easy. I told you, whatever we revise, all these sample questions, that is what you will find in any of the exams or the cards. I will not set questions from the blues. I will set what I taught the students in class. Leave alone the part of critical thinking where applicability comes in. You already have a unit on critical thinking. Let the critical thinking lecturer do his part or her part. But at this point, whatever I teach in class, that is where I'll test the student on. You can't test the student on what they were not taught. No. So if we are together in the revision sessions, everything is fine. If we are together in class, everything will be fine at last. So we are talking about disaccharides. And this one I covered the first time when I was doing disaccharides, the part for the short answered. And I don't think whether anything is complicated here. What I need to stress much on question number 20 is that at this point now, you are advancing in studying about disaccharides. You know, in the short answer, I talked about draw structure of lactose, name the glycosidic bond, and the monosaccharide components involved. That one you're also including here. Draw the structure of sucrose. Draw the structure of what? Maltose. Yes. But now you have to tell the stories behind the lactoses. Milk, sugar. We are talking about reducing sugar. It is found in milk. Lactose intolerance. Whatever we discussed based on lactose, put it there. It is needed. It's necessary. Then you go to sucrose, related to dental caries. It is the sweetest of all. Whatever. All those stories about sucrose, put it there before you can draw the structures. The malt sugar, on hydrolysis of what? Is it of starch? You'll get maltose. All those stories, they will be of help. Put all those stories and give me the structure. And here, the structure scores a lot. I always focus on the structure. And remember, I mentioned that don't just throw words in maltose. Tell me 2 glucose units. I'm not going to give you a mark. You have to specify alpha D, glucose, and beta D. We are forming the alpha 1,4 glycosidic bond for sucrose. Alpha D, glucose, and beta D, fructose, forming an alpha 1,2 glycosidic bond. Then describe everything as a non-reducing sugar. All the monosaccharide components have been involved in bonding. Explain everything about these disaccharides which you know. But then remember to include the bonds, the type of glycosidic bond, and specific monosaccharides which are there. Talk about a beta D galactose and a beta D glucose for lactose, forming a beta 1,4. Very important. Yes, because it's 20 marks, so we need to describe all which we know. Am I almost finishing? Yeah. Draw structures of all aliphatic is the same as the monoamino, monocarboxylic. So the other one, I twisted it because it was based much on the number of carbon, carboxyl and amino group. Here, I'm telling you to draw, but then based on the R side chain, because now we are talking about aliphatic and the sulfur containing. So you have to draw all, which include glycine, which include alanine, valine, leucine, isoleucine, and proline. And then for the sulfur containing, you have to draw the methionine and cysteine as well. And then you have to include the 3 and the 1 letter code. So that is how the essays come. Based on the classification of amino acids, I can talk about, you can see the nutritional classification is also down there. But let me finish with this, 21. I'm talking about the aliphatic. So based on the R side chain, they have the methyl groups. Most of them, almost all of them are hydrophobic because of the presence of the methyl groups. The sulfur containing, whether we have methionine and cysteines. Remember, the cysteines are responsible for the formation of this sulfur bridges. But then the methionine, mostly it is the one which is known as the start codon. So you'll be able to know the 3 and the 1 letter. Even here, the 3 letter code and the 1 letter code are obvious. So it's not as challenging as maybe the ones of asparagine and glutamine and tryptophan, for example. So question number 22 talks about 2 criteria which are naming of monosaccharide is based on. That one you already discussed on the board. We said the functional group, and you have to give structures also based on the number of carbon atoms in the main skeleton. Number 23 talks about classification of amino acid, nutritional classification of amino acids. And it says that any 5, meaning you have to define essential amino acids, the ones which have to be obtained from the diet. The body cannot synthesize them. And the non-essential, or I've done it the other way around, I think it's that way. The non-essential, the body can synthesize them. So each one of those classes, you can draw any 5. That's how simple it is. So you have to define the nutritional classification. You have to define the essential and non-essential amino acids. After that definition, you have to talk well about the ones which are responsible for growth. The ones, if they are not there, especially the ones which are provided by the diet, if they are not there, then it leads to growth failure. Then at that point, you need to give examples. 1-letter code, 3-letter code structure. Then you define also non-essential. 1-letter code, 3-letter code, and you'll be able to get the marks. So thank you for your time, and I wish you well as you prepare for the cut on Friday. Let us be there on time so that we can start it by 10:30. I can even come at 10 if you people are ready, but I need to give people time because I've already set and I've already printed it out. I'm just waiting for the time to come so that I can give it. But then let us start at 10:30 sharp. Let everyone be at the venue. I don't always give makeup. And I told you students, I already have the list for the ones. Yes, thank you so much. I already have the list for the ones who are going for the trip. In fact, there are only 9 students. So those are the ones which I'll give makeup. By the time we are doing cut 2, I'll give them extra time. But I will still cover where we've covered. So let us be there on time. If you miss, I'm not going to give a makeup. I'm sorry. So let us be there and hope all will be well. All the best with everything, and may God bless, and have a good night. So tomorrow you can have time to study so that by Friday, everyone is set. Thank you very, very much, my dears.